Hello everyone, my name is Sanjeet Kapadia and the topic for my seminar is Mina. So to understand why Mina is unique, it is important to understand the motivation behind creating Mina. Living in today's world requires giving up a lot of control. Every day we give up control of intimate data to large tech companies to use online services. Even when we try to escape this power imbalance and participate in blockchains, most of us give up control and trust to third parties to verify transactions. And why does this happen? This happens because running a full node requires expensive hardware, unsuitable amounts of electricity, and tons of time to sync increasingly heavier and heavier chains. So basically users want control, so they end up using blockchain. Using blockchain now ends up running an expensive node. This is not feasible and hence they end up giving control for running these nodes. So the motivation for creating Mina is to tackle this issue. Mina is a new cryptocurrency protocol which makes it possible for anyone to sync with the network on any device with full node level security while only downloading a few kilobytes of data and completing a few milliseconds of computation compared to gigabytes and gigabytes in traditional cryptocurrency protocols. Mina is the world's lightest blockchain. It is powered by its participants. By design, the entire Mina blockchain is only 22 kilobytes. And this is just the size of a couple of tweets. This allows participants to quickly sync and verify the network themselves rather than relying on other sources. So the original plan of a blockchain was to provide true decentralization, scale, and security. Mina is providing these things, especially the true decentralization. Mina is a wallet that fits in your pocket. It is the first cryptocurrency with a succinct blockchain. Its size has been compressed from hundreds of GBs down to just few kilobytes in size, as I mentioned, 22 kilobytes in size, and it allows for verification on blockchain even on a mobile phone. So there is a chart here which shows the growth rate of the size of Bitcoin. In the early stages of any particular cryptocurrency, it is relatively easy to operate a full node. As the blockchain is small, maybe just a few megabytes. However, as time goes on and more transactions are recorded, this grows to hundreds of gigabytes, as can be seen in this chart. In turn, this makes it less realistic to operate a full node without a computer designated specifically for that purpose, and it makes it impossible to run on a smartphone. So this is just a size comparison. Mina will always remain of a fixed size, whereas other blockchains are of increasing size. So no matter how many transactions are conducted, Mina's blockchain always remains of a constant size. Mina is secured by its participants. Mina is a network that enables an uncapped number of block producers via a proof of stake consensus. It is uniquely decentralized, secure, and lightweight. It gets even more secure and resilient as it grows in size, in terms of the users. Now that I have introduced what Mina is aiming to do, it is time to explain how Mina works. So what is it that makes Mina possible? So there is a three-step process for this. The first is the utilization of ZK SNARKs. I will explain exactly what ZK SNARKs are in a short time. So utilization of ZK SNARKs effectively compresses the blocks into a single proof or certificate. Now, the end users check this proof instead of checking the entire transaction history of the block. So basically the end users check the proof of the compressed block instead of checking the entire transaction history of the block. So this is an important thing to understand. Lastly, a recursive composition of these SNARKs or certificates enables a constant sized blockchain. So what are ZK SNARKs? So ZK stands for zero knowledge. ZK SNARKs are an iteration of zero knowledge proofs. It is a cryptography scheme where zero knowledge is relayed to a verifier when providing them with a proof of computation. So ZK SNARKs stand for zero knowledge, succinct, non-interactive argument of knowledge. That is what ZK SNARKs stand for. So they can function as an unforgeable certificate. And we can create, and we can create a SNARK for any computation. So at the core of the Mina protocol is the usage of ZK SNARKs, which can be used to certify any computation. ZK SNARKs that function as unforgeable certificates, they are used to prove that a computation was performed correctly without proving the entire computation. So basically, we can take any computation, such as verifying the transactions in a block, and create a SNARK out of it. This SNARK proves the accuracy of a block's transaction history without having to show all the transactions. And this effectively decreases the size of a block to a single SNARK, to the size of about a KB. So the SNARK verifies all the rules for consensus. It ensures that transactions are signed, they are valid, the consensus rules, that is the total hash power, the chain strength for proof of work, and the variable random function or the other rules for the proof of stake. So now one may think, what if the SNARK is not honestly generated? If the SNARK isn't honestly generated, it's not valid. Anyone on the network would be able to see that near instantly on something even as easy as a Raspberry Pi or a smartphone, that it won't be valid. So now that I've discussed what SNARKs are, like they seem cool, but how do we use them? So at first thought, we can think of something like this. We can create a SNARK for each block by shrinking each block into a kilobyte, right? So basically for each block we create a SNARK of it and its size will be a kilobyte. But this would still result in a linear growth as the SNARKs pile up. Out here, in this case, the blocks. Hence, we would need a better solution as this method still has a linear growth. So what is the better solution? So what if we created a SNARK of multiple SNARKs? Like, well, we know that a SNARK can be used to certify any computation, and creating a SNARK is a computation in itself. So basically, we can create a SNARK of multiple SNARKs, and using this, we can get the desired outcome, which won't have linear growth. So for example, this image here depicts multiple certificates or SNARKs that are each verified by an end user. So what exactly is a recursive composition of SNARKs in Mina? As previously mentioned, we can chain these certificates together in a recursive composition and allow the blockchain to remain of a constant size of approximately 20 kilobytes that consists of the SNARK and the tail end Merkle path. Each time a new block is produced, a new SNARK or certificate is created. So new block created implies that a new certificate is created. By creating a single SNARK comprised of the previous certificates, you are able to create a single mega SNARK in a sense that proves the entire transaction history of the blockchain, allowing you to jump from the genesis block to the current state while remaining the size of just a single certificate. Now let me give you a simple example to, to demonstrate how this works. So let's say that you have one certificate stating that you can go from block 0 to block 2. In addition, you have another certificate stating that you can go from block 2 to block 4. You could then combine these SNARKs into one single SNARK, which states that you can go from block 0 to block 4. The new SNARK or certificate remains of approximately 1 kilobytes in spite of the multiple certificates included. On a greater scale, you can create a certificate for the entire transaction history of the blockchain, which remains of a constant size. This happens despite of the number of certificates jammed into the most recent SNARK. So now the image here is an example of multiple certificates or SNARKs placed into a single SNARK. So here we can see there are multiple SNARKs placed into a single SNARK, and this SNARK is still of 1 kilobyte. So now how do we validate a node in the Mina protocol? Validating a node in Mina comprises of a recursively composed ZK SNARK of size 1 KB, which proves the validity of the entire past history of the blockchain and the Merkle root path of the current state, and the size of this is 20 kilobytes. So together proving the validity of a user's balance. So just to put it in a brief way, that a composition of the ZK SNARK that has the history of the past and the Merkle root path to the current state, together putting this would prove the validity of a user's balance. And this entire process takes only milliseconds to sync up to. So the image here is of an end user verifying a SNARK of the current state, which includes all the past certificates as well as a Merkle path. All of this comes together, allowing a user to validate their balance. So like I had said, the user first downloads a 1 KB blockchain SNARK, proving that you can reach state 4 from the Genesis, downloading 20 kilobyte Merkle path to get your account info. So that's all he has to do. That comprises of approximately 21 or 22 kilobytes, as I had mentioned at the beginning. So I will just summarize the advantages of Mina. It is easily accessible, it can be used on a browser, and it can be used on almost any device, even an old Nokia phone. And last but not least, it can connect to the internet. So the developers of this Mina protocol are focusing on three main use cases. The first one is end-to-end data privacy from online to on-chain. The second one is permissionless web oracles. The third one is one private web login. So I will just explain briefly each of these use cases. The first one, end-to-end data privacy from online to on-chain. So here, users can access critical on-chain services. On-chain means like on the blockchain, without sharing their personal data. On most chains, counterparties receive actual user data. But on Mina, counterparties receive proofs, not the data itself. This is the key part where Mina is improving the use case. And the chains that tout privacy features require users to share their data with a trusted enclave, but these are known to have vulnerabilities, and can leak data when they fail. With Mina, users never have to share their data with anyone or any entity. Instead, only the user's local machine can access their data to create a proof. The second use case is permissionless web oracles. With Mina, developers can leverage private, verified, real-world data from any website to build decentralized apps. They can input any information that is publicly available on the web without needing that website's permission. And they can access, use, and protect sensitive data by only sharing the relevant proofs. No need for trusted oracles or custom website integrations. Not only this, but Mina also allows you to connect to any public HTTPS site without needing an agreement. The last use case, one private internet login. So here, users can access any internet website or service privately without creating an account and handing over their personal data. Instead, they can log in securely with Mina. No centralized service provider can block them. And developers across chains can integrate this private secure option into their services. So these are the three main use cases where the Mina developers are working on. There are many other applications as well. So this is the end of the seminar. I would like to thank everyone for watching and for giving their time. I wanted to include a few more details but could not due to some time constraints, as explaining those things would require a lot of time together. I would also like to thank Dr. Ashutosh Bhatia and Dr. Kamlesh Tiwari for guiding me in this course and seminar. Thank you once again.